mistake, and Alexander should be right up. Here's a quick outline. So I'll start by reviewing something that all of you likely know very well, which is the heavy, light 4-point function and the associated double twist operator. Then I'm going to study these double twist operators by mapping them to a black hole, and they'll become orbits around a black hole background. So after that setup, we'll start with the supersymmetry, and we'll show how to compute the Green's function in the black hole exactly using supersymmetric gauge theory. And finally, I'll compute the OPE data for these double twist operators using the supersymmetric gauge theory. So that's where we're going. Okay, so the thing that we're interested in is the 4-point function, 2 heavy operators and 2 light operators. So H stands for heavy and L stands for light. And by light, I mean that the dimension of the light operator is much smaller than CT. And by heavy, I mean that mu, which I defined to be delta heavy over CT, is fixed. So CT goes to infinity, the delta heavy goes to infinity, and the ratio is fixed. This heavy operator is a black hole. So we can expand this in different channels. We have this channel. And in this channel, the operators that appear are powers of the stress tensor to the k. And if we expand this at small mu, this goes like mu to the k. And these contributions are universal at the minimal twist. So what I mean is that we look at powers of the stress tensor, and if you look at operators with the minimal twist for a given k, then these contributions are universal. In general, they can depend on the C. Okay, so how about the other channel? So we have heavy light, and the guys that appear here are these heavy light double twist operators, H, L, and J. And schematically, they look like this. So there's some product of H and L with some derivatives. So these operators are universal at the leading order in 1 over J. So in the large spin expansion, the leading order is universal, and beyond that, it's model dependent. And the things we're interested in for these guys are the anomalous dimensions and the OPE coefficients. So we want the dimensions of these operators, and we want the OPE coefficients. Okay. So those are the objects of interest. At mu equals 0, we have a generalized free field. And then beyond that, these things get corrected. So how do we compute these corrections? Well, there's a few ways. There's a few methods that are known. So the first one is Hamiltonian perturbation theory. Namely, we map this problem to ABS. We perturb around the ABS wave functions as a power series mu. and you solve for the dimensions and the OB coefficients. This is very hard. And by hard, I just mean computationally hard. You're going to get integrals over ADS. You're going to get hypergeometric 3f2 functions, and it's going to take you a long time. So, yeah.
Sorry, does this assume a gravity dual or?
Yeah. And so everything is holographic. Yeah, gravity dual. And if you pick a specific gravity dual, there will be a specific black hole around which you can perturb these.
And the statements you were making before about universality at minimal twist and so forth, does that also assume a gravity dual?
I don't. Well, it assumes large CT. So everything assumes large CT. So, and that, are you asking if there's if it assumes a large gap?
I think that's right.
I'm not sure. Does anyone know?
I mean, does T to the K as an operator even make sense if you only have large CT? But I take free theories. Or well, free theories it would make sense, but like perturbation.
Yeah, I think he's asking about the large gap. Yeah, I'm not sure. I'm not sure if this is universal.
I thought the question is really about what is the gravity dual, given the data you have. I mean, you're not going to use some full theory in a situation where you know the exact duality. Rather, you just need to put in some basic information like CP, and the way to just construct some effective theory, right? And that's essentially what you're describing.
Right. Any other questions about this?
Yeah, maybe you will comment about it, but just, I mean, what does it mean this heavy light double twist? Because it's a very high energy part of the spectrum, so there's lots of operators in that. So it's not really a very clean operator.
Yeah. So that's probably the key point. So it's surrounded by a black hole, but the key is, as I'll get to, if you work perturbatively in large spin expansion, these things are exact eigenstates. They're not resonances. But if you work at finite spin, they mix with black holes. So I'll describe that in a second.
So this is expansion in mu.
Yes. Okay, so another strategy is the Lorenzian inversion formula. So this is due to Yuzhou and Zheng also. And this works at finite spin, which is nice. But so far, it's not known how to get the finite spin answer beyond order u. And a third way is make an ansatz for T to K. And solve proxy. So this is due to the doubling group. And it's very nice and it's very powerful. But it only works order by order in the large spin expansion. We want to know how to compute these things to all orders in the large spin expansion.
Sorry, I have a stupid question.
Yep.
If it's an expansion in mu, typically in perturbation field, then you want to be able to tune this parameter to 0, whereas then you say it's fixed. In order to have a controlled perturbation theory.
It's fixed, but it can be small.
Yeah, but if you tune it to 0, then CT could be infinite times bigger than that height, right?
Yeah, it's an order of limit. You can think of it like having a small black hole.
Okay, so you will take mu to 0 then?
Yeah.
Okay. So that's a bit misleading.
Okay, great. So how are we going to do this? So what I'll do is I'll map this mu expansion to the instanton expansion in an SU2 gauge theory in 4 dimensions. And this will give us a simple algebraic equation for these deltas, and you can solve it order by order for mu. And then you can. I'll also describe a procedure for computing these these OBE coefficients from the instanton expansion. So that's hopefully where we're going. Okay. But before getting there, we have to address the question about the resonances. So are these things, what's the bulk interpretation of these heavy light double twist operators, and are they stable? Great. So let's first recall these light double twist operators. So this is now in pure ADS. We have two light operators, and they're circling around each other in some kind of binary orbit system. So we have a light operator, and they're just circling. And N is going to label the eccentricity of this orbit, and J is going to label this thing. So, by analogy, since this heavy operator is a black hole, maybe this operator, this heavy light double twist, is a black hole surrounded by an orbiting particle. And again, the guess is that N is going to be related to the eccentricity, and J is going to be related to the spin. So let's make this more precise. So I'm going to write the metric. And I'm also going to take a limit, which is where the mass of this light operator is much greater than 1. So that means that the wave function of the particle in ADS is going to be well localized on the orbit, so there's a good semi-classical description of the orbit. So M light is much bigger than 1. And I'll take ADS 5. Here it's not so important whether I take ADS 5. Sorry. But later it'll be very important. So this is the redshift factor. So here mu is Newton's constant times the mass of the black hole in units of the ADS radius. Okay, so we have this orbit, and we need to solve the geodesic equations. And they take this form. So here E and L are the conserved energy and angular momentum of this orbit. And the final equation is R dot squared equals E squared minus V of R. So V of R is V of R equals F of R times L squared over R squared plus 1. And so this is like a particle moving in a potential. And the potential looks like this. So this is for sufficiently large angular momentum out. This potential develops a stable minimum. And so we can just solve for that minimum to find the position of a circular orbit. And what you get is as follows. So these are the energy and the angular momentum as a function of the radius. Okay. And now we just solve for E of L. So E of L equal to L plus 1 minus mu over 2L plus order mu squared. So we have the energy as a function of mu as an expansion of mu, and at mu equals 0, this is the equation for a circular orbit in ADS, and then there are higher corrections. So on the boundary, we define J equals delta light L, and delta equals, sorry, I should not do that. Okay, so this is the spin, J as a function of the angular momentum, and the dimension of this operator is equal to the heavy dimension plus the energy of the orbit, which is this. And we can repackage this as delta heavy plus delta light plus J plus gamma. So here, gamma is going to vanish at mu equals 0 because this is the free expansion in ADS of this operator, and in particular, what you find is that this anomalous dimension gamma is equal to minus delta light squared mu over 2J plus order mu squared. So this matches the results from these three methods that I mentioned before. In the limit, where delta light goes to infinity, and also J goes to infinity, and the ratio is fixed. So that's the semi-classical limit, where the wave function is concentrated around the orbit. It's possible to compute systematic corrections to that limit using the Bohr-Sommerfeld rule, but that would take me too far afield. Great. Okay, so that was circular orbits. So I'm not going to say anything about non-circular orbits. I'll just draw the potential in that case. So again, we have this potential, and now we have oscillations. Three turning points: RC, RB, and RA, and the orbit can oscillate around the middle. So recall that we had these light double twist operators in ADS, and those things are stable. There's no obvious decay process for them to decay, but the black hole situation is quite different because the particle can either tunnel into the black hole or it can radiate gravity waves. So at CT equals infinity, there's no radiation, and we can just look at tunneling, and we can write down the tunneling amplitude. So the tunneling rate for tunneling over this barrier is as follows. So this is just the action. Let me see if, yeah, I got it right. And
Sorry,
yes.
you cannot pass.
I think so.
Oh.
Camera cannot see beyond this.
Oh, I thought that was there. Not as a I was like, why don't I just move this?
It's okay.
The viewers at home need to see the whole equation. Move it first. Okay, so you can evaluate this integral. So this is the tunneling over the potential barrier. And the key point is that this is going to be non-perturbatively small and at large spin. So for large black holes, mu is much bigger than 1. It looks like this. And also J much bigger than mu. And for small black holes, it goes like mu to the J, where mu is much less than 1, and J is much bigger than 1. So in both cases, this is non-perturbatively small at J. So what does this mean? So it means that since these orbit states are unstable to tunneling, we shouldn't think of them as eigenstates. We should think of them as resonances whose complex energy has a small imaginary part. So there's a name for that in the black hole. It's called the quasi-normal mode. So a quasi-normal mode is defined like this. So it's a solution to the wave equation. Okay, so that's the wave equation. It's ingoing at the horizon. And finally, it's normalizing. Okay. So if there's a solution that satisfies these conditions, then there's a quasi-normal mode at that complex value of the energy. So another way to think about these quasi-normal modes is that they're poles of the retarded Green's function.
Sorry, I'm a bit confused.
Yeah.
This is fully classical, or is there anything quantum about this kind?
Quantum.
This is fully classical, right?
Yes, yes.
So it's classical graphs without
Yeah, yeah. So CT equals infinity, but yeah, I mean, it's quantum mechanics in it, yes.
It's really a quantum tunneling process.
Yeah.
Of a particle. But sorry, where is G Newton in that gamma?
It's hidden in mu because mu is G Newton times the mass of the black hole, which is fixed.
Just a, sorry, a very silly question. Okay, I understand. Okay.
Thanks. Okay, so we can also think of these things as poles of the retarded Green's function, and to confirm this, indeed, the quasi-normal modes have the following values. So this was shown a while ago by Festuccia and Liu. Plus gamma minus I gamma of tau. So the real part is this is just the energy of the orbit as a function of mu, and then you have the imaginary part, which is due to tunneling. And as I said before, tunneling is non-perturbative at large J. So at large J, we can just think of these large spin eigenstates as these large spin quasi-normal modes as eigenstates. And that's the way to think about these heavy light double twist operators. So that's all the background I need. Perfect. And now we can get into the details.
sorry, so the punchline in the language of CFT, are there eigenstates with this energy, with an approximate, there are eigenstates with an energy which is approximately the first line, right? Without the item.
Yeah, they're black holes. Yeah.
Why do you say they are black holes? They are the black hole plus the particle, or
Well, I mean,
they have an overlap with the state in the black hole.
yeah, but I thought you were asking approximately this energy. So, I mean, there are always black holes that are very, very close to the energy of the. Because the spectrum is so dense.
I'm not sure why you.
The spectrum is there, right?
Yeah.
Solid is black holes, or black holes is the gas.
Yeah.
I mean,
I would think of these resonances as a superposition of black hole microstates over a small range of entities. Makes sense? No?
What's the difference between the sun and the earth? Is it the same or not? That you would also say that it's a sun, that we are a sun, the formation of the sun. I mean, the particle can be, right? It can be a big thing, right?
Oh,
It doesn't
yes,
need to be a
yes.
very small thing, so it can be the earth, right?
Yes, yes.
And the black hole can be the sun. So then,
But the system is unstable. So the way to think about it is the black hole plus the orbit is an unstable system. I mean, eventually the orbit's going to fall in, and it's going to make a bigger black hole. So that means that there's mixing with black holes that are very close to that energy.
Isn't this just due to the mixing between double trace operators and some single trace operators with large density of states? Right?
Yeah, it should be.
It's expected.
Okay. Well, let's go on to supersymmetry. So what's the strategy for computing the OPE data? Well, we see that these things are just poles of the retarded Green's function. So maybe we should compute the retarded Green's function. So we want to compute the exact GR. And then look for poles. Okay, so now I'm going to write down the wave equation, and I'm going to write it in some unfamiliar variables. It might take a little bit, so I'll narrate as I go. So this is going to be a differential equation with 4 regular singular points. It's going to be one at 0, one at z equals t, one at z equals infinity, and one at z equals 1. So an equation of this type is called the Heinen equation. And it has a bunch of parameters. These AIs are associated to each of the singularities, and it has this finite parameter u. So I'm writing this just because it's the fundamental object involved in what I'm studying. Okay, great. So there's some map between the black hole parameters and this equation. I'm only going to write one of the maps that's going to be important. So this parameter t.
Sorry, so chi is GR. So I mean, the solution GR solves these equations.
I'll get there in just one second. So the one thing that I'll write down is that in terms of the black hole horizon radius, t is given by this formula, and the crucial thing here is that at small r plus for small black holes, this thing is going to scale up. So the T expansion is going to be like a mu. Okay, so now to answer your question, how do we compute GR as if we know how to solve this equation? So a couple. So Z equals T is the horizon, and Z equals 1 is the boundary. So we were told how to compute the retarded Green's function by summing star nets, among others. And what they tell us is to do the following. Take a solution to this equation, which is ingoing at the horizon. So what this means is that it goes like this. So this is just in terms of these A parameters, but it's easy to see that this is the ingoing solution at the horizon. And then we take the solution and we expand it at the boundary.
What is U?
U is just one of the parameters. It's defined in terms of the frequency, the angular momentum in this mode, and so this is the Fourier space. It's in the gauge theory. Well, we'll get there. So now we take this thing and we expand it near the boundary. So there are two behaviors near the boundary. So there's one source and there's one response, and this is what that looks like in terms of these A parameters, even though I haven't told you what they are. And so once we know this, the retarded Green's function is given by the response over the source.
Sorry, I should have asked this before. I realize now. Why is it the retarded Green's function and not any other Green's function that we are studying?
Well, I think you can get any of them. But, I mean, the way to see it from this equation is this thing is going to have poles when A vanishes. And when A vanishes, that means that the source vanishes, so we have a normalizable mode. So the poles of this thing correspond to normalizable ingoing modes at the horizon, which in turn correspond to quasi-normal modes.
I mean, it's finite temperature, right? So normally there, in any given state, there are only two point functions that are independent, and at finite temperature you can just relate them with usual Boltzmann factors and so on.
Right.
So retarded is easy because that corresponds to causal evolution in the bulk, and so you just take ingoing boundary conditions are relatively easy to impose, so let's do that one.
Thank you, yes. Okay, so what this means that what we really need is, in a mathematical sense, is we need to know the connection coefficients of the Heinen equation. The connection coefficients relate solutions near one singularity of an equation to solutions near the other singularity, near another singularity, and that's exactly what we want. So, how do you solve that problem?
So before you go there, maybe you can say something. Is this some special coordinate? Is Z that
Yes.
uniting Schwarzschild? Yes, not.
Yeah, I'm sorry. So,
Is this some?
so Z is going to be, it's not a torus coordinate, which I understand is confusing. Nope. That looks good, yeah. So at r equals 0, Z equals 0. At r equals infinity, Z equals 1. And at r equals r plus, hopefully Z equals t. It does. Great. Any other questions? Okay, so how do we compute the connection coefficients of the Heinen equation? The strategy is it spans decades worth of papers, which I won't even try to summarize, even if I did understand them. So instead, what I'll do is just write out 5 steps. Let me mention the work of Alba Grassi, who pointed out the connection of this wave equation to supersymmetry, along with her collaborators, and also my other collaborators, Christopher Ayusa and Daniel Liftig, who solved the problem of computing the connection coefficients. So those are a couple of developments in this direction. So I'm just going to summarize this train of thought in 5 steps. So we consider the following 5-point function in Liouville field theory. I'll continue here. So what this guy is going to be a 5-point function of 4 primaries and 1 degenerate field of level 2. And this satisfies a BPZ equation because it has a degenerate operator. Okay, so that's step 1. Step 2, take C to infinity. C here being the central charge of the Liouville theory. And in this limit, BPZ becomes 1. If you don't take this limit, this actually satisfies a PDE. But when you take this limit, it becomes an ODE, which is the Heinen equation. Excellent. Step 3. Write the crossing equation for this 5-point function in a couple different channels. And what this does is it gives relations between Virasoro blocks in different channels. Okay, 4 is use AGT. So what this does is it maps the Virasoro blocks to a supersymmetric gauge theory. In our case, we have 4 singularities. So it's going to be an SU2 gauge theory with 4 hypers. In the fundamental. Okay. And the partition function of this thing is just known exactly due to Nekrasov and Shadishvili. There's an additional limit that needs to be taken that corresponds to the C to infinity limit, and that's on the gauge theory side. That's called the Nekrasov Shadishvili limit. But these things are known. The partition function of this theory is given as an instanton expansion, and the coefficients are you can write them down exactly.
So what's the dimension of this SU2 gauge theory?
4 dimensions.
4 dimensions. And the Levinian is 2D, Levinian 2D. Okay.
42. And then finally, we use step 3 and crossing between different channels gives the connection coefficients. Okay, so that's a long story. But all we need is formula, so why don't we just take it from their paper? So now I'm going to write down the exact Green's function. Are there any questions about this train of thought? I can try to answer them maybe.
Maybe just is there any reason why this is giving you? I mean, is there any physical reason why this system is governed by an equation which has anything to do with qubit theory and AGT and blah blah blah?
Not to my knowledge. It's a nice. We're very lucky that. I mean, in some sense, we know that the wave equation is going to have some regular singularities, hopefully. And in D equals 4, it happens to have 4 of them. And the general differential equation with 4 singularities is this one equation. So it's almost guaranteed. But I don't think that there's any physics behind it.
Is the reason why you consider ADS5 is to make use of this formula? Or?
Yeah, I'll mention a little bit about higher dimensions. It's going to be a more general AGT. Okay, so now let's write down the formula. Okay, so this is going to take a while also, but nice to be able to write it down. Okay, so this is GR is a function of the frequency and the spin. R plus is the horizon radius. F is the instanton free energy of this gauge theory, and then we're going to have a sum. M minus sigma. M minus sigma. AT A 0. M minus sigma plus A 0 A infinity T to the sigma A e to the minus sigma over 2 DAF. And then, so this is in the numerator. So this is what I called B before, and then A is going to be very similar. So. So this is the full thing. I haven't told you what A is or what M is, so let me do M first. So M is going to be defined in terms of gamma functions.
Sorry, can I ask a question
Yes.
so that I see where we are? So
Yes.
at this point, we could forget about CFT and just say we are studying quasi-normal modes of a black hole, right?
Yeah.
And this black hole turns out to be an ADS. And of course, there are hundreds of papers about quasi-normal modes. The new thing here is that you are going to use some correspondence to AGT to do things more analytically than before.
Yeah. So.
Or is it that it was in ADS? Can you put it in context in the middle of all this quasi-normal mode literature?
Yeah. So. Albagrassi and collaborators had a paper a couple of years ago where they did the AGT analysis in flat space. So in that case, it's not quite point. But they get a quantization condition for the quasi-normal modes, which is going to hold exactly. In our case, it's going to be much. We also get a similar Green's function. It's going to be a bit nicer because the instanton expansion is going to map to the mu expansion. And there's not a similar thing in flat space. So the part that's new here is going to be the map of the mu expansion to this instanton expansion. So it's like a strategy for computing quasi-normal modes that works in ADS.
And before, those quasi-normal modes were studied numerically, and now you can compute it analytically and match the first ones. Is this the case?
Yeah.
Can you say what is the intuition for mu being related to the mu expansion being the instant expansion?
Intuition. Sorry. What is the intuition? an iteration.
But isn't it because it's exponentially suppressed?
Because what?
It's because is it because it's about exponentials? Right? This gamma was exponential, instantons are exponentials. Is it just that, or it's more subtle than that? The other corrections, I guess, are probably not exponential. Right?
Yeah, I don't think they're exponential. No. Yeah, but that's the mapping between the parameters. So.
Yeah, I guess, I mean, usually in the bootstrap business, we tend to want to use, we see there are sort of blocks that tracing things like recursion relation, but here it seems that this alternative way to compute it, the advantage is precisely that it has this manifest instant expansions.
Exactly, yeah. So yeah, as we'll see, everything, we get very lucky that the instanton expansion is also the luck from bootstrap expansion. Okay, let me just finish writing this. Sorry. Anyway, it's not important. Okay, so this is these are some gamma functions, and okay, so these A's are I wrote before in the Horn equation. I haven't told you what A with no subscript is. So what that thing is
Sorry, can I ask?
Yes.
So you mentioned something about flat space, that someone had tried to do something similar in flat space.
Yeah.
Can you repeat what it is?
So there's no dimensionless parameter of U in flat space. So there's not going to be a similar expansion in that case. It's related to the fact that in ADS, a large spin is like going far away from the black hole. But yeah, so the paper is by Grossi and friends, and they write down a quantization condition for the Quasi-Normal modes, but you can't really go anywhere with it. There's no expansion that you can make.
But people measure Quasi-Normal modes in flat space, right? They study Quasi-Normal modes.
Yeah, so you can compare numerically, but there's no analytic expansion parameter like there is in this case, which is mu. But yeah, it works numerically for sure. I'm not sure if I followed the question, sorry.
No, it's not their fault. I am lost a bit.
Okay, well,
This knowledge of Quasi-Normal modes.
yeah.
So in flat space, you say there's no parameter mu, but people do compute Quasi-Normal modes. So
Yeah, you can look for the
it's not a
lowest.
problem, right?
Well, yeah, so there's not going to be an analytic expansion of these things, but you can look for the Quasi-Normal modes at a given spin, and you can look for them numerically by just solving the wave equation, and you can find them. Okay, the final thing I need to tell you is what this A is with no subscript, and it's defined by something called the quantum Hamiltonian relation. It's part of this AGT stuff, and that's I think the final formula we need. Okay, so U was in the original Horn equation. AT, A0, A1, and A2. Sorry. AT, A0, A infinity were in the Horn equation. And the final parameter is A, which can be computed from this relation. Okay, so the dictionary between black hole and gauge theory. So these parameters A0, A1, AT, and infinity map to the masses of hypers. T T maps to e to the minus 1 over g mil squared, which is the instanton counting parameter. And A maps to the vet of a scalar in the theory. Okay, so that's the map. Let me briefly mention some properties. It can be studied numerically. So we can take this expansion and then expand order by order in T and truncate the answer at order, say, T to the 7. And you can show that this converges very quickly to the correct Green's function. So another comment is that at large J and fixed spin, J goes to infinity. Sorry, at large J and fixed omega, these blocks simplify, and we can use a Zone-logical formula for the conformal blocks to compute these things exactly in this J to infinity limit. And what you find is that the imaginary part of GR is like e to the minus c times j as j goes to infinity, and c matches some other calculation of the imaginary part. So that's like the Zone-logical regime of these Green's function. But that's not what I want to talk about. I want to finish now by saying how to compute these double twist OPE data. All right. So I wrote an exact formula, and recall, even though I just erased it, that it had a factor t to the sigma n. And there was a sum over sigma equals plus or minus 1. So at small t and therefore small mu, what you find is that t to the minus a goes like mu to the j. And this is exponentially small in spin. And so if we neglect all non-perturbative corrections, as we said we were going to do, we're left with the perturbative in spin regime, which is like the regime where the double twist operators are exact energy eigenstates. And then things simplify a lot. So I'll call this GR pert, because it's perturbative, and it looks like this. I don't have to write the denominator, but there's also a denominator. And there's some more gamma functions. So there's gamma. So this is a lot simpler. It still involves this free energy, but things have simplified a lot. And in particular, we can just find the poles. The poles, it turns out that in the small mu expansion, the poles come from this vacuum. And so these are just the poles of a gamma function. So that's the full answer. Yes.
Could you differentiate a bit more the classes from the T?
Sorry?
If you can differentiate more
Yes,
class
yes,
from
yes,
T
yes.
when you write it sometimes.
Yes. Oh, that's really bad. Thank you. Good. So what do I want? No, plus.
Sorry, the perturbative, you mean the perturbative in large span?
Yeah. So that's the regime where tunneling is 0.
Mm-hmm.
Okay, so this is the answer. And I told you what A is. It can be solved from this formula. We know what F is. It has an expansion in terms of Young tableau, and so you can just plug it into Mathematica, and it takes maybe 20 minutes to compute up to fifth order in mu, and it agrees with everything that's known. And it can be done to any order in mu also. So this is an algebraic equation which can be solved perturbatively in mu. And similarly, for the OP, so this is for omega and j, and for the OP coefficients, so the square of the OP coefficients I call C and J, and these are related to the residue of GR at omega and J. And both things agree. With Bootstrap. Good. Okay, so the final thing I want to say is remember we had this argument that these double twists are actually unstable at finer spin, and they're unstable due to tunneling. So how do we see the tunneling?
Sorry, did you explain why the residue is the OP coefficient?
Yeah, so it's because of the relation between the retard-Green's function and the Whiteman function, because the Whiteman function is the imaginary part of the retard-Green's function, and so you pick up the residue of the pole, and that gives the 4-point function that we want. Okay, so just a quick reminder, how I got here was I neglected all these terms, but now we want to expand to first order in those terms to find the imaginary. And so if you expand the exact formula to first order in t to the minus a, you'll find the imaginary part of omega and j. So as j goes to infinity, this agrees with the tunneling calculation, and then there's some order one, order one correction there. So everything seems to come out of this exact formula. Okay, so let me conclude with some future directions.
Sorry,
unless there are questions, yes.
Maybe question. So the formula you wrote there, it looks a bit like the GR acts like OP density from the inversion formula. Is there any connection, or it's just next things?
Maybe.
Okay.
I'm not sure, sorry.
Thanks.
Any other questions before I conclude?
Can you comment a little bit on the flat space limit? Well,
Yeah, so this, well, in some sense, the small black hole, well, yeah, sorry. Yeah, the small black hole limit is not quite the flat space limit, because you can have a small black hole and then go right. So, indeed, the flat space limit can be taken. You have to scale, so you have to scale delta light goes to infinity. You have to do something with mu also. I don't recall the precise combination that you take them to zero in, but these equations do have a flat space limit, which gives the answer for an orbital in an asymptotically flat black hole.
so let me ask maybe the question a bit differently. So you emphasized at some point that mu was very useful because you want to measure things in units of the ADS radius, right?
Yeah.
So, but in ADS, of course, we don't have ADS radius. Can you remind us what sets the scale for this quasi-normal modes? Yeah, what replaces mu
in flat space? In flat space. Right. Yeah. I guess it's going to be. Yeah.
You still have mass in flat space, right?
Yeah, you still have mass. Yeah. Yeah, I guess it's just the mass of the particle.
mass of the particle.
Or do you have one with the black hole?
It should be dimensions.
The mass of black hole.
Sorry, we have a dimensionless ratio, which is the mass of the particle over the mass of the black hole.
That's the parameter.
Um, yeah,
I thought it had nothing to do with the mass of the particle. No? Am I confusing things? But I thought quasi-normal modes were these things that measure the tails of these gravity waves, etc.
well, but they're defined from massive scalars also. So they're going to be different. I mean, for instance, delta light, the dimension of the light operator enters the answer for the quasi-normal modes in ADS. Yeah, I'm sorry, I'm just blanking out on the flat space limit, but it's in our paper, so I can maybe look at it and tell you later. Sorry.
I mean, before the tunneling, in flat space we have something like the hydrogen atom. And there's some potential barrier, and then it goes to 0 to infinity.
Yeah.
So it's not plugging up with R, so you cannot
Yes.
scale down the energies.
Yes.
So then the question is, what is fixing the energy difference in the levels of the hydrogen atom, which is probably just mass of the particle. So in that case, there's not an actual parameter because it's energy for mass and the number or something like that. Negative.
That's not correct. Yeah, I can look at the formulas again. All right, so let me conclude. So here's a few questions that would be interesting. So somebody asked about other dimensions. So d equals 4 is very, very simple because it's this one equation. If you go outside of that, if you go to any other dimension, there are more singularities. So we still get a differential equation with all regular singularities, but now there can be n of them. And this maps to a linear SU2 curve on the AG2 side. So again, it can be studied. It would also be interested to study hydrodynamics. Maybe that expansion becomes simpler once we know the exact Green's function, although not much progress yet. And something.
By hydrodynamics, you mean the higher derivative correction?
So I mean the limit of the Green's function where omega and k go. Omega and sorry. You take the infinite volume limit and then you send omega and the momentum to 0.
And then you try to measure transport coefficient.
Yeah, but that expansion is not very natural from the instanton expansion. It turns out that in the infinite volume limit, t, the instanton parameter, is 1/2. So I don't know what to do with that, but it's possible that there's something to do there. And finally, there's some interesting mathematical structure in the other channel, in the heavy goes to the light channel, that was pointed out by the Dublin group, and they have some conjectures about certain coefficients of logs in the stress tensor blocks, and they're related to numbers associated to Young tableau, which also show up in F. So there's some interesting connection there to be understood better. Otherwise, I'll stop there and thank you for your time.
Question?
So in all this business, you are discussing a light operator and an heavy operator,
Yeah.
and then you are putting angular momentum, extrinsic angular momentum, right? That just rotates the two objects. why don't we need to worry about small back reactions, giving us a little bit of angular momentum to the black hole or to the light state? Why is it enough to just think of?
I think those are whenever CT is suppressed, and I'm at infinite CT.
Can you explain why? Why is that true?
Well, the spin that you add to the black hole is going to be much less than its mass, so it's going to be 1/CT suppressed compared to its mass.
Maybe let me rephrase my question. Are we computing really a 3-point function, or is it a sum rule of many 3-point functions that are nearby,
I see.
possible one?
Yeah, so I see the question, thank you. In the perturbative limit at large J, it's a 3-point function, because in that limit we should treat these things as exact energy eigenstates. Beyond that limit, indeed, there's going to be black holes that are nearby. These things are resonances, and there are going to be some averages of 3-point functions.
And these are averages over states that have total angular momentum J, and the dominant one, the angular momentum is extrinsic, but around that one there are some which have a little bit of intrinsic angular momentum as well.
Well,
or that's not true.
The one that has the orbit circulating the black hole is it's not an eigenstate. So we really just have a sum of the black holes in the full non-perturbative picture. But somehow this sum of the black holes reproduces this resonance which looks like an orbit circulating black hole.
So if I understand correctly, part of the motivation to study this was to see if there was some universal sector in higher dimensional CFTs associated with the stress tensor.
Thank you. I didn't say that.
Do you have any?
Yeah, exactly. So this thing here, right. So this thing here, in the light goes to heavy channel, as I said before. We just have T to the K in the middle. So that's conjectured to be kind of an analog of the Virasoro block in higher dimensions, and this gives an exact expression for that because we've thrown away everything that's not T to the K in the light channel. So to what extent it's universal? Well, it's not going to be. This is an Einstein gravity. Away from the minimal twists, it's not universal, but it can be computed, and it's given by this formula. So this sums all the T to the K's.
So you're suggesting that you can also study higher curvature corrections and
yeah. I don't know if you can do exactly, but yeah, you can consider a higher curvature black hole and then try to solve the wave equation. Probably can't do it exactly. Like a Gauss-Bonnet black hole is not going to be exactly solved.
So I have some questions.
Yes.
So, still interesting in the fastest limit is that. So, can you take what limit you can take so that you can reproduce the quasi-normal modes in graph space? It's a twist goes to infinity, or?
That was a question that was asked before that I can't remember the answer to.
Okay.
I'm sorry.
No problem. And still, and another question is that so when we study heavy light, we interpret it as the heavy operator is a sort of a black hole in the bulk,
Yes.
but it's really not necessary. You can be adding like non-trivial background rather than black hole because you only probe the asymptotic region of the geometry. But now you're calculating the quasi-normal modes, where the quasi-normal modes really probe the region very near horizon.
Oh, no, sorry, these large J guys
Oh, this is,
are,
okay.
are very, very,
But you
far.
still have the boundary, but you still impose the boundary condition at horizon, right?
Yeah,
And
but,
how to make everything consistent.
yeah, exactly, so, by throwing away all the mu to the J's, it actually, this perturbative Green's function, does not know about the boundary conditions.
Oh, I see. Mhm.
Yeah, in the light channel, it's like throwing away all the light double twists.
So all the boundary condition near the horizon enters in the non-perturbative region.
Exactly.
Any other questions? So before we finish, so that you listen to me, I think there is a small change. The place where we will have lunch is not in the usual tent. It's closer to the actual rooms where we have some discussions. I think in front of that, I believe. Should be easy to find.
For the people who are interested, could you say what?
Come with us.
It's in that direction.